Hello everyone, welcome to this challenge question walkthrough for Edexcel's Pure Year 2 textbook chapter 6. Okay, our first question is from exercise 6a, and we've got the point P that lies on the unit circle centre O, and the radius OP makes an acute angle of theta with the positive x-axis. The tangent to the circle at P intersects the coordinate axes at the points A and B. And for part A, we're asked to prove that OB equals sec theta. So first of all, we can note that the angle OPB is going to be a right angle because OP is a radius and AB is a tangent at P. So if we look at the triangle OPB here, if we're trying to find the length OB, let's call that x, then we can use the trig ratio cos, and that will give us the adjacent side, which is 1, over the hypotenuse, which is x. And if we rearrange, then we're going to get x equals 1 over cos theta, so x equals sec theta, as required. And now if we look for part B, for OA, if we call that length y, and we now have a look at the triangle OAP, again we're going to have a right angle here. And now if we try and work out an angle in this triangle, well, we know this angle here is going to be 90 minus theta, so this angle up here is going to be theta. And here we can use sine. So we have sine of theta equals the opposite side, which is the 1 here, over the hypotenuse, which is y. And so we have, if we rearrange, y equals 1 over sine theta, so y equals cosec theta. And finally, for part C, we need to prove that the length AP equals cot theta. So we know that the length OA is cosec theta now. So to find the length AP, we can now use Pythagoras on the triangle OAP. So if we call the length AP Z, then we're going to have the hypotenuse, which is cosec squared theta, being equal to the squares of the other two sides, so 1 squared plus Z squared. So if we rearrange, then we're going to get the length Z that we want being equal to the square root of cosec squared theta, take away 1. Now what we can do is we can rewrite cosec squared theta as 1 over sine squared theta, and then write this as one fraction. So multiplying the 1 by sine squared theta and dividing by sine squared theta, we can get 1 take away sine squared theta over sine squared theta. And we know that 1 take away sine squared theta is equal to cos squared theta from our identities. And then from here, we can take the square root of both the numerator and the denominator to get cos theta over sine theta, which equals cot theta, as required. Okay, and our final question from exercise 6e. Part A asks us to sketch the graph of y equals sec of x with the restricted domain 0 is less than or equal to x is less than or equal to pi, with x not being equal to pi over 2. So if we first have a look at the graph of y equals cos of x, knowing that y equals sec of x is 1 over cos of x, then the graph of y equals cos of x between 0 and pi looks something like this. Okay, here is where x equals pi over 2. So if we now try and think about what the graph of y equals sec of x or 1 over cos of x looks like in this domain, then it suddenly makes sense why x can't be equal to pi over 2, because at that point we have cos of pi over 2 being equal to 0, and we can't divide by 0. Okay. So what we've done is we started at cos of x being equal to 1, and 1 over 1 at that point is 1. Then we're decreasing the value all the way up until 0, and if we're dividing by a smaller number on the denominator, then our function will increase. And what we end up with is a shape that looks something like this. Okay, and then we're going to have an asymptote where we have x being equal to pi over 2, And for the second half of the graph, what we're going from 0 all the way down to -1. So around here, where the values of cos of x are very small and negative, if we have 1 over something less than 1 that's very small and negative, so for example minus 0.001, now will give us -1000. So we can see that we're going to approach the asymptote like this. So where we have really small and negative values of cos of x around here, we're going to have very negative values of sec of x, and then this will increase up to a point where we have the minimum of cos at -1. Okay. Now for part B. Given that arc sec of x is the inverse function of sec of x between 0 and pi, with x not being equal to pi over 2, sketch the graph of y equals arc sec of x and state the range of arc sec of x. So to find the graph of the inverse function of any function, what we can do is we can reflect the function in the line y equals x. Okay, so if we do that for the graph of y equals sec of x to find the graph of y equals arc sec of x, then we're going to get something that looks a little bit like this. So we're going to have this point here, which used to be at 0, 1, now being at 1, 0 on the new graph, so somewhere here. So that's the point 1, 0. And then this point here, which is at the end of the domain, so where x equals pi, sec of x is equal to -1. So on this new graph, we're going to have the point -1 pi, so somewhere up here. Okay. Now, if we just reflect this now, so looking at this part of the graph here, being reflected will look something like this. And then the other half of the graph, which I'll draw in green here, that reflected will look something like this. Okay, where we have that asymptote, which I'll draw in purple, where y now equals pi over 2, rather than x being equal to pi over 2 on the previous graph. Now, if we look at the range of this, then we can see we have every value between 0 and -1 apart from pi over 2. So what we can say is the range is 0 is less than or equal to y is less than or equal to pi for y not being equal to pi over 2, where we have that asymptote. And that is the end of the challenge question walkthrough for chapter 6. I hope you enjoyed this one, and I will see you in the next one.